we'll discuss some problems related to digital electronics. These problems are asked in the topic memory. So in this problem, for the NMOS logic gate shown in the figure, the logic function implemented is. So for the given logic circuit, we are supposed to find what is the logic function it is going to implement. So we already know that for an NMOS circuitry, okay, for an NMOS circuitry or PMOS or an CMOS circuitry, the expression, the logical expression will be expressed as, okay, logical function will be expressed as a complement of the SOP expression. Okay. For any NMOS or PMOS or CMOS circuitry, okay. So the expression will be given as SOP expression, which is be in complemented form. Okay, in complemented form. Okay, so it will be like this. So we have to find the SOP expression here. So the SOP expression is under the product terms. Okay, product terms 1, 2, can be any number. Okay, but in the complemented. Okay, so these product terms are nothing but the parallel paths. Okay, each product terms is nothing but the parallel path from the output terminal. So this is your output terminal. From the output terminal with respect to the ground. Okay, so each product term is nothing but which are arranged in parallel paths between the output node and the ground. So now we'll see how many parallel paths are there between the output terminal and the ground. Okay, so now if you see here, so this is your output terminal, right? And this is the ground. So we have one parallel path, you have two parallel paths, and third you have three parallel paths. So therefore, your function f is equal to, okay, first parallel path. That is your product 1, second parallel path, which is nothing but product 2, and your third parallel path, which is nothing but your product 3. Okay, so this will be complement. Okay, so first we are going to write for the first parallel path. I am going to write this as P1. Okay, so this is P2 and this is P3. Okay, so parallel path between the output terminal and the ground. Okay, now, so what is the first parallel path between what are the transistors? A and B. So first parallel P1 is going to be A, B. Okay, second parallel path is going to be A and C. Okay, plus the third parallel path is going to be D and E. Okay, D and E. Okay, and all this is an SOP. This is your SOP expression, which is complementary. Complementary. Okay, so now this expression can be further written as or further simplified as, I'm going to take this A term common. Okay, so A taking common, A into B plus C plus D, E. So this is your final answer. So which matches up with A into B plus C plus D. So C is your correct answer. Moving to the next question. Moving to the next question. The output Y of the circuit shown in the figure. Okay, almost similarly, same model. Okay, so as we already discussed, we are going to write the uh, SOP expression in complemented form with respect to your output terminal to ground. Okay, with respect to output terminal to ground. Okay, so first, so F is equal to, okay, I'm going to write the SOP expression in complemented form. First, so how many parallel paths do you have with respect to output terminal to ground? So only one parallel path. So only one parallel path. So this can be written as A, B, C. This is C dash. C dash, the whole dash. Okay. So this can, so using De Morgan theorem, using De Morgan theorem, this can be further written as F is equal to, so A becomes A dash, B, so into becomes plus, B becomes B dash, again into becomes, yeah, into becomes again plus. So C becomes C double dash. Okay, so this C dash becomes C. Okay, so this is your final expression. So which matches with A. Okay, so A dash plus B dash plus C. So this is your right answer. Moving to the next question. Okay, so the logic functionality realized by the circuit shown below here. Okay, so we have to uh, find what is the logic function this circuit is going to implement. Okay, fine. So now here all the transistors are an NMOS. Okay. Here all transistors are NMOS. Okay, and we know that when input to the gate is 0, input to the gate is 0, NMOS behaves as an open circuit. And similarly, when an input to the gate is 1, yeah, gate is 1, NMOS behaves as an so this is the basic function that you have to Remember. Fine. So now, mm, so now we can we are going to redraw the above circuit like this. Okay. So above circuit can be redrawn as like this. So this is a terminal B. Okay. And this is the terminal A. And output Y. So this is transistor T1 and this is the transistor T2. Fine. So the above circuit I have redrawn like this for easy understanding. So these are the two terminals V and B dash. B and B dash is terminal A. So fine, this is the output terminal Y. So now, as we know that when input to the gate is 0, and NMOS behaves as an open circuit. Okay, so now case 1. So I'll take this circuit here. This is case 1. Okay, case 1. Okay, so here, if B is equal to 0, what will going to happen? When B is equal to 0, what happens is transistor T2 is short circuited. Okay, it is short circuited. Therefore, output Y is equal to 0. So, the output Y is equal to 0. So, we'll check it out. So, when B is equal to 0 here, so when B is equal to 0, what's going to happen? So as I already told you, when input to the gate is 0, NMOS behaves as an open circuit. Okay, it's open circuit in the sense this becomes open circuit. So what will happen to your Y? Okay, so Y is going to be equal to 0. Okay, because you don't have any connection between your input A, S, and Y. So therefore, Y is equal to 0. And similarly, the second case. In case 2. Okay, in case 2. Okay, in case 2 if B is equal to 1. Then B is equal to 1. What will happen to your transistor T1? T1 is short circuited. Okay, T1 is short circuited and the output is going to be Y is equal to A. Output Y is equal to A. Okay, so check this out. So now when B is equal to 1, so we're going to put this is equal to 1. So when this is equal to 1, so your transistor T1. So when this is equal to 1, what will happen to your NMOS? is going to be short circuited. It will be like this. It becomes short circuited. Okay. So what will happen? So this A appears as the output terminal. So Y is equal to A. Okay. So now we'll check it out. So now with the two terminals A and B. Okay. So these are the two inputs A and B with output Y. Okay. So what are the possible combinations? 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So now if you see here, when B equal to 0, Y is equal to 0. When B equal to 0, Y is equal to 0. Okay. When B equal to 0, also since it's open circuit, you don't have any output. So Y is equal to 0. So when B equal to 0, Y is equal to 0. And similarly, when B is equal to 1, Y is equal to A. When B is equal to 1, so B is equal to 1. Right here, Y is equal to A. What is Y equal to A? That means here it is 0, so here also it is 0. Here it is 1, here also it is 1. Okay, so now this logic, this truth table resembles to what? Resembles to an AND gate. Okay, when all inputs are high, the output is high. Resembles to an AND gate. So your logic functionality is an AND gate. Okay, that's fine. Then we'll move to the next one. So next question, the logic function f of x, y realized by the given circuit is the logic function. So similarly, almost the same question. So I have to find what is the logic function. This diagram is representing. Okay. So now we'll check it out. First, we'll consider this is nothing but an NMOS circuit. Okay. Okay. So first we are going to consider this NMOS circuit, and the inputs are the inputs of f of x comma y is equal to. Okay. As I already told you, it's nothing but n complemented function of the SOP expression. Okay, complemented function of the SOP expression. So here, so this is your output terminal and this is your ground. So we are going to write the expression for the NMOS circuit with respect to the output terminal to the ground. So here, if you see what is your SOP expression is, here what is your SOP? So you have two parallel branches. You have one parallel branch and this is your second parallel branch. Okay. So now first I will try the first one. So what is the input for this? Input for this is x dash and input for this is y dash. And similarly, the input for this is x and input for this is y. So now we'll write the SOP expression. Okay. So for the first parallel branch, this is nothing but x dash y dash. Okay. And the second parallel branch, it is x. And this is in complement. Okay, got it. So this expression can be, okay. So this expression can be written as x dash y dash plus xy is nothing but x dash y dash plus xy is nothing but x x nor y. Okay. So the whole dash. Okay. So this can be further written as uh, okay. So this can be further written as x x or y. Understood? So your final answer is nothing but x. Okay. So now we move to the next question. So now here we are going to discuss a PLA problem here. Okay, PLA problem. So in this problem, the question is given as a programmable logic array is shown in the figure. The Boolean function f implemented here. Boolean function f implemented here. Fine. So now here we are going to find first going to find the product terms for the three product terms. First, so we'll take like this. So I'm going to take this as x1, and take this as x2, and this as fine. So now first, so as we know that in PLA is nothing but we have an underarray or array. So here in PLA, both underarray and array both are programmable. So we have in PLD we have three main classifications from. Okay, so in PLD, programmable logic device. Okay, PLD we have three main classifications from, PLA, and PAL. PAL. So PLD consists of underarray and array. PLD consists of underarray and underarray and array. Okay. So based on the underarray and array, how it can be programmed, it is classified into three: from, PLA, and PAL. Okay. So here in PROM only array is programmed. Only array is programmed. In PLA, both array and underarray both are programmable. Array and underarray both are programmable. In a PAL, only underarray is programmable. Only and array is programmed. Okay, so you can easily remember like this with this word. In from, you see, okay, O. O refers to R, and middle word A refers to and. Okay, so by this and the PLA is both. Okay, so that you will have an clear idea which is program. Fine. So here, so now we have, so this function f is going to have three product terms x1, x2, and x3. Okay, now from this we are going to write what is the product term for x1. So x1 is nothing but, see here, p dash q r, p dash q r, and x2 is equal to p dash q dash, p dash q r, p dash q r. Got it. So x3 is equal to p q dash r, p q dash and r. Okay. So now therefore a function f is equal to addition of all this, p dash q dash r, p dash q dash r plus p dash q r plus p q dash r, which matches up with c. Okay, matches up with the c option. So now move to the next question. Okay. So now, in this circuit shown, A and B are the inputs. Okay. A and B are the inputs, and F is the output. So what is the functionality of this circuit? So what is the logic function is going to implement? Okay. So in order to find the answer for this, so input B, so if you see, then input B is connected to the input B is connected to, so I will put the transistor as this as A. Okay, I'll put this transistor as A for your understanding. I will put as T1 and T2. Okay, T1 and T2. So input B is connected to the transistor T1 and input A is connected to the transistor T2. So now input so input B. Input B is connected to the NMOS transistor. That is NMOS transistor. Here I mentioned it as T1. Okay, NMOS transistor contrast T1. So what will be the status of the transistor? Okay, so if B is high, so if B is high, So see, repeat. So your input B is connected to the transistor, NMOS transistor T1, and if if your input B is high, okay, this is high, you can see your output F is connected to your is connected to A. F is connected to A. So already we know that. Okay. So already we have discussed this here in the previous column. Okay. See here. So the input. Okay. So here when you give high here, B is high, what happens? NMOS behaves as a short circuit. NMOS. So when B is equal to 1 here, what happens? This behaves as a short circuit. Okay. So what happens? So F is connected to the A. This is what I'm trying to tell you. Okay. So in short, that's nothing but that is nothing but when if B is equal to 1, F is equal to D. Fine. Okay. Similarly, okay. Similarly, input A is connected to the input input A is connected to the NMOS transistor T2. Okay. Similarly, input A is connected to the NMOS transistor T2. So now if A is equal to 1, what will happen? Okay. Okay. Similarly, if A is high, A is high, okay, what happens? This becomes short circuit. So F is connected to the B. Okay, F is connected to B. So that is similarly, that is if A is equal to 1, F is equal to B. Okay, right? And now, if both the inputs are A and B are 0, okay, if both inputs A and B are 0, what will happen? So if both inputs are 0, so this is A also if it is 0 and B also it is 0, what will happen? It will be an open circuit. Okay, so this will be an open circuit and this will also be an open circuit. So F is equal to 0. Okay, so F is equal to V equal to 0. So now we'll check this with our truth table. So we have two inputs A and B is the output. So the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. Fine. So now, if B is equal to 1, F is equal to A. When B is equal to 1, okay, okay, B is equal to 1, F is equal to A. F is equal to A. A is 0 here, and this 1 here. Similarly, if A is equal to 1, F is equal to B. Okay. When A is equal to 1, F is equal to B. F is equal to 0. So it is 0 here, and you can see 1 is 1. Fine. And when both are 0, when both are 0, so what is going to happen? So this is not equal to 0 here. Okay. And both are open circuit. Okay. This is, okay, open circuit. So what happens here is VDD appears at the output. So both are open circuit. So what happens? Your VDD appears at the output. So it's going to be 1. So this truth table resembles to an okay XNOR. Your option is D. Understood? And we'll solve one more problem. So for the circuit shown in the figure, P and Q. Okay, for the circuit shown in the figure with inputs P and Q, okay, with and output Y. What is the logic implemented by the circuit? So the same type. Okay. So all the you know that so in the PMOS circuit, conduct at logic 0. And NMOS conduct logic 1. Okay, logic 1. So now you will see case 1. You will see two cases. So in case 1, if P is equal to 1, what will happen? When your input P is equal to 1, and this is equal to 1, so what will happen? We have two MOSFETs. We have PMOS, here NMOS. So when P is equal to 1, what happens here? When P is equal to 1, and then the PMOS conduct? No, doesn't conduct. Okay, so it does not conduct. So that means it is as put is an off condition. And the NMOS conduct. Okay, and P is equal to 1, what happens? NMOS conduct, and this does not conduct. Okay, so this NMOS will be in on condition. So what is therefore here Y is equal to? So what happens? So this is not going to conduct, and this is going to conduct, right? So what happens here? So we can agree. So Y is equal to Q dash. Y is equal to Q dash. Next, case 2. Case 2, P is equal to 0. P is equal to 0. So we'll see what is the condition of P mass and the N mass. So when P is equal to 0, the P mass will be on and N mass will be off. Okay. So during that time, so P mass will be on and N mass will be off. So what happens? The Q will appear at the output. So Y is equal to Q. So now we look at the truth table. So with two inputs, P, Q, and output Y. 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So now, when P equal to 1, Y is equal to Q dash. When P is equal to 1, when P is equal to 1, okay, Y is equal to Q dash. Y is equal to Q dash. 0 becomes 1, 1 becomes 0. And when P is equal to 0, okay, when P is equal to 0, Y is equal to Q. So just write that 0 and 1. So this resembles as an XOR. Therefore, a function Y is equal to P XOR Q. Nothing but is an XOR operation. Okay, understood? So we'll stop video at this. We'll continue in the next week.